All right. Good morning, folks. Welcome back. I didn't see anyone yesterday. I apologize. I had a quick meeting that well, it wasn't quick, but I had a meeting I had to go to right after the exam. And so if you did try to come back, I apologize. I did get back a little bit later than I thought. If you have any questions, feel free to pause the video now, come on back into class and get your questions answered. Okay, if not, stop by after my seventh period class today and get your questions answered about projectile motion, whatever questions you may have about what we've done in class so far. Okay, so please make sure you get your questions answered. Don't hesitate to get your questions answered now, and don't put it off. Okay. All right. Let me go ahead then and let's continue on. I'm sorry, by the way, I'll try to do then is on either Monday or Tuesday of next week. There will be one more FET lab, another FET lab that I'd like you to do that'll help you with what I've with projectile motion here, how you should approach the problem, and give you a little bit of hands-on in doing the FET lab. I'm sorry, doing projectile motion. Okay, so that will be hopefully Monday, if not Tuesday of next week. I do want to go ahead and get done with the discussion of projectile motion first, and then we'll get started with it. Okay, so that'll kind of expect that early next week. Okay. All right, so with that said, let me go ahead and let me share. Let me open up my screen here, and let's go ahead and let's take a look, use this to review where we left off with on Tuesday. Okay. So we finished up projectile motion is an object that's moving in two directions, is a motion in which an object is moving in two directions at one time. It's moving horizontally and vertically at the same time. The motion that we've been examining, this parabolic motion, has the object moving forward along the x-axis and then up and then back down. Now you can easily have the object move in the backward direction and then up and down, but we're going to focus in on the forward direction. And so if you notice them, with all of the horizontal vectors, all of the x component vectors, okay, they've all been positive. They've all been positive. They've been all pointing towards the right. And if you look at this screen here, you've noticed then that with the velocities, they're all going to be positive. And when we talked about displacement, and I derived that for you, those were all positive as well in terms of the x direction, in terms of the horizontal. Okay? So again, we've been looking at the forward motion here, but again, like I said, projectile motion can go in the opposite direction as well, and thus have a negative displacement, negative velocity for the horizontal portion of that motion. Okay, so what we did is we wrapped that up, and we talked about how then you can use the one kinematic equation that's going to tie all of them together. It's the one where we had velocity is equal to the displacement, or displacement is equal to the initial velocity times time. If you like, come on by after school today, and I'll revisit that with you. But make sure you keep that in mind. That's how we can solve then for the horizontal displacement of an object that is moving in this projectile manner. Okay, so that's what you want to make sure you keep in mind. The horizontal component, the horizontal motion, the horizontal component of this projectile motion is pretty straightforward. Now, what you want to make sure you keep in mind as you go through these problems is that and the FET lab, and this is the reason why I want us to do the FET lab, the FET lab will help reinforce this point here. And that is, whenever you have projectile motion, you want to make sure you separate the motion out into its horizontal motion and the vertical motion and treat those separately. Okay. And there is one factor, and I've been hinting at this. There's been one factor that will tie both of those motions together, and I'll mention that towards the end of this. Okay. All right. So we focused in on the horizontal motion. Let's start talking about, let's finish up with the discussion of the vertical motion. Okay. All right, so the first thing we have to remember about the motion, the vertical motion, is that there is an acceleration along the y, okay, and that we define that as the gravitational acceleration. Remember, g is negative 9.8 meters per second squared. And the reason why we have an acceleration in the y direction along the vertical is because the only force that we were saying that's going to act on this object, and this is, again, remember the vertical motion. We're talking about the vertical motion here. Okay. And so when we talk about the vertical motion here, we have an acceleration. Okay, we have single acceleration, and that's the reason why then is that the only force, so therefore we were talking about the sum of the forces, okay, The only force acting on this object as it moves is going to be gravitational force. Okay? And so because of that, we will see then that the object moving in this manner will change the way it moves, again, vertically, not horizontally. It will change the way it moves vertically. And we saw then that change in this manner, and that we saw, and we were able to trace this, that as the object moves upward, the upward trajectory, as the object moves upward, we see then that that its velocity it gets smaller and smaller. That means that it slows down. Okay? So as it moves up, it's going to slow down. It's going to change the way it moves as it moves up. Then we saw this. That's the upward trajectory. And then we saw then in the downward path, in the downward trajectory, we see then that the object then starts to speed up. And we were able to identify this because as it moves up, its velocity is going to be positive. But remember, acceleration is always going to be negative. The acceleration then, which is g, will be negative. And so the signs are opposite. And whenever the velocity and the acceleration have opposite signs, we learned this back in chapter 3, it's going to slow down. The object's going to slow down. Whereas with the downward trajectory, if you take a look at this, then the arrows change direction. The arrows change direction. So now the velocity is negative. It's pointing down. The acceleration will always be negative. That's always pointing down. And so therefore, the object speeds up. So only along the vertical motion, or only along the vertical portion of this projectile motion here, will the object change the way it moves. Okay? And that's what you want to make sure you keep in mind. Okay? And so as we go through this then, what we're going to see then is that there's some other key points that you want to keep in mind then in terms of the velocity. So if you notice here, the velocity is going to get smaller and smaller, so it slows down, and we see the arrows increase as it goes, and so as it goes up, it's going to slow down, and we see the arrow then increasing as it goes in this downward trajectory, okay? And therefore it's going to slow down. However, the velocity at the very top, and if we take a look at this here, okay, if we take a look at this, the velocity at the very top is 0, which means then, and again, only in the y direction, okay, as it moves up, that is where it will stop. And the way you want to treat this horizontal motion, the way you want to approach the vertical motion here is that you want to treat it as if it were in free fall. This is an object that is in free fall, okay? And treat it like a object that is free falling. And we learned about the free fall back in chapter 3. Remember, back in chapter 3, when we talked about the free fall, we said then that in order for an object to be free falling, the way we define it, and kind of simplify it, is that the object has no other force acting on it but gravity. Remember, we're ignoring air friction and everything else. And that's exactly how we describe them, the vertical portion of projectile motion. Okay, and so when it reaches the very top of its pathway, that's when it has to stop, and then it turns around and comes back down. Remember, with the free fall, remember an object going straight up has to stop before it comes back down. And if you draw it that way, as you look at this, that looks almost like the parabolic motion that I have represented for you here. Okay, and so treat the vertical component, treat the vertical portion of the projectile motion. Okay, treat the vertical component portion of it as if the object is in free fall. Okay, and so that's what you want to make sure you do with the velocities. Okay? And then with the initial velocity here, okay, we can go ahead then and we can find then the y component of that initial velocity. We saw this as well by looking at this and solving for the sine, take the initial velocity and find the sine and multiply that by the initial velocity here. And you want to make sure you keep that in mind in order to get this initial velocity. Okay? And typically you'll be given this, and you'll see, we're going to try to work through a problem today where you'll see this, and you can solve for that one. Okay. All right. So with that said, that's the motion, and that's what we have. Okay. And what we want to make sure we always want to do is we want to make sure then that we always treat the upward direction as positive, downward as negative. Okay. All right. So those are the velocities. Now we know how to deal with the velocities. Let's deal with the displacement. Okay. And so we did the same thing with the initial horizontal motion. And what we want to be able to say then, is if you can imagine this is the ground right here, okay, how far did the object travel up at this point? That is, we want to find then the displacement at this point here, which we will call then delta y. Okay, so that's the displacement at the first point here. What would be the displacement here, how far did it travel up? So we're trying to find that here, not how far it's traveled out, but the height of the object at each one of these points here. So at time, so this will be time 0 here, initial time. At time is equal to 1 second out, how far up has it moved? What's the height of the object at that point? What is the height of the object at this second point here, which is going to be at time 2? Okay, and excuse me, sorry. This represents the peak. Okay, the height of the pathway, that's when it reaches the apex. And that's going to be a unique point that we're going to keep in mind then. And then as we continue on, how far is it up at each one of these points here, or at any point on this pathway, can we find the displacement of each one of these here? Okay, so at each one, I'm sorry, let me call it, let me highlight another point here. Can we find how far up the object has moved, and then we'll call this T3, at each one of these time intervals here? So this T3, sorry, this will be T4. Okay. And so that's the key there. Okay. And so how do we go ahead and go about doing that? Okay. Well, that's where we will have to rely on the kinematic equations. Okay? And let's take a look at the kinematic equations, and let's see how we can obtain that. Okay. Let's imagine that we have it. So we know the acceleration is constant. So the kinematic equations, remember, relate motion of objects that have constant, or what we call uniform acceleration. The object moving in projected motion absolutely has uniform acceleration. It has a constant acceleration. It is this. It's negative 9.8 meters per second squared. So with that said then, if we wanted to find the displacement here, we wanted to find the displacement, okay, what would we need to know? Well, in the first equation then, okay, if we know then 1/2, and let me go and write this down. If we know the initial velocity, okay, the final velocity, okay, and time, okay, we should be able to define then we should be able to find then the displacement. Okay, so the initial velocity then would be the velocity at time 0 right here. Okay, and then that's where this is going to be important here. So we can calculate for delta v naught y right here, and then we can find the velocity at this point here. That'll be, we can then, and if we know the time interval between t0 and t1, we can find this displacement. Okay, so again, if we know the initial velocity here, so this would be v initial y, okay, and if we can find the velocity at this point right here, where we were called, so this is the time interval that we are observing from t0 to t1, so that's our time interval. If we know the velocities at this point, we can go ahead then and we can solve then for that displacement. So that's one of the kinematic equations that we can use. There's another kinematic equation that allows us to find that displacement. Okay, and we had then, and we used it, which is v initial times time plus 1/2 a t squared. So again, looking at the two time intervals here, and this will apply to any of these intervals here. Okay, so if we know the initial velocity right here, okay, at the time is equal to 0, if we know the time interval here between t initial and t final, which is t1 right here, okay, in order to find this delta y right here, this displacement, all we need to know then also is the acceleration, and we do. Because the acceleration is constant, we know then that this is going to be g. So we can go ahead and use this equation to find how far up, how high up the object has gone at this moment in time. Okay, so we can use the kinematic equation to get that. And we had a third equation that allows us to solve for displacement. Okay, and that was then we had then v. I'm sorry, v. Sorry, I'm going to do this here. V final squared is equal to v initial squared plus 2a delta y. Okay, all right. So if we know, so using this equation here, if we know the final velocity, the velocity at this point here, and if we know the velocity at this initial point here, okay, we can find this displacement as long as we know the acceleration. And again, we can get that. So again, all we need to be able to do to solve for displacement is find the velocities at these points up here. Okay? If we know what those velocities are, if they're unknown, if we can try to find it, and I'm going to talk about how in just a moment we can find those. Okay, if we can find those velocities, the y component of those velocities, we should be able to use any of these kinematic equations here to get the displacement, how high up the object has gone. Now there is a way that we can calculate for it, okay? And let's go ahead and let's take a look at the fourth kinematic equation here. And that is we had then V final is equal to V initial plus A times T. Okay, so if we needed this final velocity here, if we know the initial velocity and if we know the acceleration, and again, we do, we know this acceleration here, we don't have to solve for it because it will always be negative 9.8 meters per second. All we need to do then is measure this time interval right here, plug that in, we can solve for V final. Okay, and once we have V final, we can use any one of these equations now to solve then for this displacement. So we can use the kinematic equations, all four of these kinematic equations, which I will give you. So all four of these kinematic equations, we can go ahead and use now in order to solve then for this displacement. Okay, so three of them will give us the displacement, and the fourth one will allow us to solve for that final velocity if we need it, so that we can solve for the displacement. Okay, so you have to remember how to use these kinematic equations in order to solve then for displacement. Okay. All right, so that's how we get displacement. We already know how to obtain the velocities for the motion for an object moving in this projectile manner here. Okay. Now let's go ahead then and let's let me go ahead and save this really quickly for you. Okay. Let's go ahead then, and so this is how we would solve for V final kinematically. Okay, using the kinematic equations. Okay. What if we can find these velocities at other points in the projectile, in this projectile manner? Okay, using trig, can we do that? Okay, and the answer should be absolutely yes. We can use trig in order to find this because at any moment, at any point on that projectile motion, then we should be able to find the velocity at that point if we know the x and the y components. Okay, all right, so let's go ahead then, and let me go ahead and show you how this is done. Okay. So let me go ahead then, and so we want to be able to find the velocity, not the let's go ahead and get this done. And I want to point, let's do that for a couple of them here. Okay, let's go ahead then and let's find the velocity at that point. That is, we're going to try to find the red arrow right here. Okay, so we're going to try to find the velocity at that point. The velocity at that point, okay, is up and towards the right, which puts it in the quadrant, in the first quadrant. Okay, it puts it in the first quadrant. All right, so let's go ahead and draw that arrow really quickly. So this is the velocity vector right there. Okay, if we can find, and if we know how to get, okay, if we can find then the x component, okay, if we can find the x component at that point, at this moment in time here. So let me go ahead and actually mark that as well. Okay, so we want to find the velocity here, okay, at time, and let's call this time 1, okay, t1. Okay. If we want to find the velocity at that point, now again, we're not trying to find the y or the x component of this velocity. I'm going to show you that we already know that, okay, or we can obtain that fairly easily. Okay, we want to find what that actual velocity is. The actual velocity is up and towards the right. Okay, so we need to find this velocity here. If we know the x component at this point at time t here, and if we know the y component at time t there, we should be able to, because they form a right triangle, use the Pythagorean theorem to find this velocity right here. This is the unknown velocity right here. That is, what's the velocity? What is this velocity at time t is equal to t1? Okay. All right, so we should be able to do that. And furthermore, we should be able to describe then the angle at which it's a trajectory angle, okay, at that point, the velocity at that point. Okay. So with that said, do we know, can we calculate, and do we know what the initial velocity is? So we need to know what the x component of this velocity is. Okay? And the answer is absolutely, we do know that, because the x component of the velocity here at this point is exactly the same as the initial velocity along the x. Why? Because along the horizontal, the velocity along the x never changes. The velocity never changes along the horizontal. So therefore, at this point here, that velocity is equal to the initial velocity. We don't need to do any other trig to get that done. Okay, so that's what you need to make sure you keep in mind. Okay. So with that said, then, can we obtain the y component of the velocity here? And the answer there is also yes. Okay, using one of the kinematic equations, we can use, depending on what we know, we can use the kinematic equations to get the velocity at that point. And that's why we need to know what the kinematic equations are. Okay, and so once we have that, so this is how we would go about trying to find the velocity at any point on the pathway. So if we wanted to find the velocity at let's say this arbitrary point right here, okay, we would need to know a few things. We would need to know, for example, let's say we need to know the displacement. So we would have to get the displacement from along the horizontal. Okay, we need to know that displacement. So we can get the displacement there. We can get the delta y there. If we know the time interval, okay, that is how long it takes to get there, we'll call this t2. Okay. Then we would need that for the y component. Okay, we would not need that for the x component. The x component of that velocity at this point here, which would be down and towards the right, which would be put it into the fourth quadrant. Okay. The x component never changes. Along this pathway here, the x component will never change. We would need to know the displacement, the time, okay, in order to find then the y component at that point. So really, the only work that we need to do is we need to be able to find the y components. Okay, we need to find the y components because remember the y components change. The x component, the velocity along the x never changes. It's the velocity along the y. The vertical velocity always changes. The horizontal velocity never changes. Okay, and that's what makes things a little bit easier. Okay, all right. So once we have that, then I think it's pretty straightforward. Okay, once we've done this calculation, then finding then v then requires us simply. Whoops, sorry. Let me go into this. Okay, finding v then simply requires us to, and I highlighted in the previous slide for you, but I'll write it here for you. To find then the velocity at that point, we just need to take the Pythagorean theorem, take vx, square that, and add it to vy and square that. And once we have that, okay. How would we find this angle right here? We now have vx and vy. We could take the inverse tangent vy over vx and get our angle right there. Okay, and so that's how we would go about solving then for the velocities, and not the components again. Make sure you understand that we're not solving for the components. We're actually finding these velocities here. We're trying to find these velocities here, okay? And we should be able to attain that working it out this way. Okay, so you'll get a chance to practice, but make sure you keep in mind that that's how we'll go about finding the velocities that are not the initial velocity here nor the final velocity here. Okay, all right, very good. Let's go ahead then. And let me just summarize this up for you, and then I want to try to work through a problem with you in order to give you some practice, so that you can. I'll assign some homework over the weekend. Tomorrow, I'll assign it to you get to practice. Okay? All right. So summing up what we talked about so far, okay, with the with projectile motion. Okay? We got to ignore air resistance. Okay, and if we ignore air resistance, then the first thing you want to make sure you keep in mind then is that the acceleration along the horizontal, AX, okay, is always going to be 0. That's going to be 0 meters per second squared, which means then if we ignore air resistance and the only force that we are considering in projectile motion is gravity, then what we have then is that we have one acceleration, and that's going to be acceleration, the gravitational acceleration, what we call then that free fall acceleration, which is g, okay, which is going to be negative 9.8 meters per second squared. Furthermore, the acceleration at the top of the trajectory, at the very top of the pathway, okay, is not 0. The acceleration is always going to be negative 9.8 meters per second squared, downward, because we don't have any acceleration along the horizontal, and we only have acceleration along the vertical. The acceleration will always be the same along the vertical motion, and that's always going to be downward. So even as it moves up, acceleration is down. When it reaches the top where it stops, remember the velocity at the very height there is going to be 0. The velocity is 0 at the top. Okay, and again, it's the velocity on the vertical that is 0, not along the horizontal. Okay, so even at the very top where the velocity along the vertical is 0, the acceleration is still downward. So please make sure you keep that in mind. That's something, again, I think I've mentioned this already, that in the past I've seen it asked once on the AP exam, the AP physics exam. So that's a point that a lot of people miss and they forget. Okay, all right, so those are some things you have to remember also for projectile motion. Okay, the vertical component, okay, we talked about this. Um, we can use that to find the displacement along the vertical, okay? And we can do that using, just keeping in mind that if you treat that vertical motion as a free fall, an object in free fall, using the kinematic equations should be pretty straightforward, okay? All right, so with that said then, what you want to make sure you do then is you want to treat the motions along the vertical motion and the horizontal motion independently. You want to treat them independent of each other and treat it as if they are, you have an object that's moving only along the horizontal, horizontally along the x direction, and then treat it as if the object is moving only vertically. Okay? And so that's what you want to make sure you keep in mind as you go through this. Okay. All right, so with that said, then the launch angle, the projection angle, we can solve then using the inverse tangent here. Okay. And then we can use that actually also to find then the angle of the velocity at any point along that motion. Okay. So the key here then is treat the two motions separately, okay, the x and the y separately, and that's something that if you can't remember anything else about this lesson today, make sure you keep that in mind. Okay, that, and also at the very height of the motion, that the acceleration there is negative 9.8 meters per second squared. Okay. All right, the last thing I want to point out to you then, and there is one last thing that we can use here to help you to solve these problems, and that involves then the how the object moves itself. Okay, so let's take a look at this here. Okay, so I have here for you a diagram where you have an object that's going to be shot up into the air in a projectile manner. So we know that this is projectile motion because we see that parabola right there. Okay, and then you can imagine this is kind of being an object being shot up above a cliff and then falling down below the cliff. So you can imagine then that this is a cliff right here, this is the cliff, and then below you fall below the cliff here to get to the ground below. Okay, so you shoot an object up in the air. Okay, so here then is the initial velocity right here. This is the launch angle right here, which we call alpha. And here is the y component of initial velocity and the x component of the initial velocity. Okay? We said then at the very top of this motion right here, at this point, I'm sorry, at this point right here, arrow, okay, at this point right here, okay, we have then the object reaching its height. So therefore, the velocity on the y is going to be 0 meters per second. Okay, and this represents then the height the pathway, that is the delta y max. Okay, and I'm gonna write this as the maximum height, the maximum delta y, that is the height that it's gonna reach. Okay, okay, and then that's where it starts its ascent at this point here. Okay, all right, I want to focus in on, and we're gonna stop it right here for right now. Okay, I want to focus in on this here. If you take a look at this motion then, and you can imagine this line right here splitting this this parabola in half, you have what the left half and the right half be exactly equal to one another, which means then we have symmetrical motion. Okay, there's symmetry here. So if you draw a line straight down here, the left side of the parabola is exactly the same as the right side. There's a symmetry that we have there. Okay, and we can take advantage of that. We can use that to our advantage. Why is that? Because when the object reaches this point here, when the object reaches this point here, right before it falls below the line, okay, right before it falls below the line, at this point right here, okay, something happens that is we can use to our advantage. Okay, at this point right there, and so we call this V initial right here, and we call at this point here, and I want to draw this for you. Okay, V final then is going to remember it's going to be following in that direction. There is V final, which follows roughly that pathway right there. Okay, so at this point here, V final, okay, okay, is going to be equal to V initial. Okay, so the magnitude V at this point here, the initial velocity and the final velocity are going to be exactly equal to one another, with the one exception in terms of magnitude. This is going to be negative. Okay? And that is something you can use to your advantage. And as long as the motion is symmetrical, okay, the velocity at this point here, which we refer to as the final velocity, is going to be exactly equal to the initial velocity. It's just going to be in the opposite direction. And that's what we have right there. Okay? And so that is one key characteristic. That's the first key characteristic of symmetrical motion. Okay, so if you can identify that the object is moving in a symmetrical manner, okay, you can say that. There is one other advantage you can take advantage of here. Okay, and that is in terms of the time interval. the time interval that it takes the object to move from there to that point, which is I refer to as the time it takes to go up. Okay, so this is going to be time up. The time it takes to go up. That's what this is going to be time to move up to the top. Okay, and the time it takes to come back down. Okay, and so this time interval right here, which I will define then as t down. Okay, and so this is the time. Oops, sorry. Okay, so this is the time interval. This is how much time it takes to come back down to the same, so back down to the same level that it started out at. Okay, and this is the time to move down. Okay, what can we say about those two? And I think hopefully the arrows you can already see there. Okay, the time that takes to go up is going to be exactly equal to the time it takes to go down. And that's if it's symmetrical. Okay, that is before it falls below that point. And this is the second key characteristic of an object that is moving in a symmetrical manner. You can use these two here to your advantage to make solving these problems much easier and much approach solving these problems much more efficiently. Okay, so you have to first of all identify that you have an object that is moving in a projectile manner, moving along this parabola, okay, and that there is symmetry, that there's symmetry to it. And if it's a parabola, folks, if it's moving in a projectile manner, you're going to get that. You're going to get. I'm sorry, if it moves in that parabolic manner that we see right here, you're going to have symmetrical motion. That will always be the case. And if that is the case for symmetrical motion, you have these two characteristics, these two key components of symmetrical motion that's going to help you solve for these problems, for solving for the problem that we'll be doing in just a moment. Okay. All right. Very good. Let me go ahead then. Let me save this and let's take a look at then how we would go about solving for the problems involving projectile motion. Okay. First thing I would suggest you do is draw the picture. Now, this is not a free body diagram, but I would suggest you just quickly draw that parabola. Okay. And then what you want to do then is that you want to make sure that you include the initial and final positions. Okay, include whatever information they give you. I would also write in there, I would remind myself that the acceleration is going to be g, and I'm going to talk about that. Okay, and then what you should do then, so that's the first thing. You want to draw the picture, sketch it, and then include all the information onto that sketch that is either given to you or that you already know because you know what the characteristics of projectile motion are. And so, should you memorize them? If you need to, you can, but I would argue that by doing these problems and doing enough of them, you will memorize what the characteristics are of projectile motion. So you don't have to. Okay, so but you do need to remember them, and you need to. And I would suggest initially, at least, you write them down. Okay. All right. And then what you want to do then is with the initial velocity, and this, if they give it to you, when it says resolve, that just means then solve then for the x and the y component of the initial velocity. Okay. And typically in these problems, you will see then that they will give you the initial velocity. Okay? So the initial velocity, remember, is not the x component or the y component of initial velocity. That's the velocity that the launch velocity and with the launch angle for the object. Okay, and so when it says resolve, then it simply means then to solve then for the x and y component of that initial velocity, and then go ahead and then you can start solving for the problem and treat them separately. Okay. Treat displacement along the x and displacement along the y, solve for those separately. Okay, and then at the end, if you need to bring it back together, you can. The one component of these problems that will be the same that that is not independent is time. Time is the one component here that will be the same for both the x and the y direction. Okay, for the x and the y direction, and so make sure you keep that in mind. Okay. All right, so those are the things. Then what you want to do then is use the kinematic equations, okay, to solve then for either the horizontal or the vertical motion. With the horizontal motion, remember, since the velocity is constant, solving for that displacement becomes very simple because there's this one equation that you will need to solve for that displacement. Okay. Whereas with the motion along the y direction, the vertical motion, you want to make sure then that you're going to use all of the kinematic equations to help you solve for it. Okay. All right. So with that said, let me go ahead then and let me ask you to take a look at this problem right here. And what we'll do is I'm running low on time here. So what I'm going to do then is in the lesson for tomorrow, I'm going to work out this problem. I'm going to work out this problem for you, and then we will go ahead. Whoops, sorry. I'll work out this problem for you, and I will use this problem to help you review projectile motion, and then review all the procedures that we will need to use in order to solve for problems like this. And hopefully, please make sure you take a look at this problem and recognize that this is an object that is moving in a parabolic manner. This long jumper is moving in that parabolic manner that is characteristic, that is the key characteristic of projectile motion. Okay. All right. So please come by. So that's it. So we've gone over what projectile motion is. Now what we want to do is we want to apply what we know to solving for problems like this. Okay. And my hope then is, again, like I said, we'll work through more of these problems tomorrow in tomorrow's lesson. And then it looks like right now on Monday, it'll be Monday where I'll assign the PhET lab to you, and I'd like you to use what you know about projectile motion to work through that PhET lab. Okay. All right. Very good, folks. Please stop by and get your questions answered if you have any, or stick around after I take roll tomorrow and get your questions answered. We can even go over, start going over these problems as well. Okay, but you'll see it in the lesson tomorrow. Okay. All right. Have a good rest of your day, folks, and I will see you tomorrow in class for roll. Okay.